So we can think about solution formation as happening in 3 steps. We've got separating the solute into particles. That's always going to be endothermic because you've got intermolecular forces that are holding them together that need to be broken. So delta H for separating the solute is going to be greater than 0. And then we have separating the solvent particles to make room for the solute to come in. That's also going to be endothermic. So delta H for the solvent is going to be greater than 0. And then mixing them is going to be exothermic because we'll have some energy released as new intermolecular forces form. There's always going to be some form of intermolecular attraction, even if it's only dispersion forces. So this will be less than 0, the heat of mixing, but this might be a very small number. And so what we're going to look at is the relative amounts of, or the relative sizes of those. So we call that the enthalpy of solution. So the energy involved in making a solution from these 2 things. It's going to be the sum of the changes in enthalpy for each step. The overall sign of the enthalpy of solution is going to depend on the magnitudes of those different individual terms. And so solution formation can be exothermic or it can be endothermic. It's depending on the relative strengths of those intermolecular forces. So here, this kind of looks like those Bohr-Haber cycle diagrams, doesn't it? It's the same idea. So here we have the solvent aggregated, meaning it's stuck together like it's supposed to be. Here we have the solute aggregated. And so one step that we think of is separating the solute into individual particles. And so that requires energy. Going up, we have to put energy in. And separating the solvent to leave some room for the solute molecules, that also requires energy. When we mix these, there will be some gain in energy. This will be a negative because as these mix, they're forming new interactions. And so for this illustration, the net process is exothermic, meaning it's giving off energy when it mixes. In this illustration, it's going to be endothermic. Again, we're separating the solute particles, we're separating the solvent particles, we're mixing them together, but this time the heat of mixing is less than the sum of separating these 2 together. And so this ends up being an endothermic process, and for this to mix, it actually absorbs energy. Any questions? Some solutions become warm when you mix them, and some get cold when you mix them. This solution would become cool. It would get colder when you mixed it, because it would be pulling energy in from the surroundings. This would most likely become warmer and be giving energy off to the surroundings, because that energy has to go somewhere, and this energy has to come from somewhere. When we're talking about ionic compounds mixed in water, which is what we talk about the most, we can combine the heat of the solvent, which was the energy required to separate the solvent particles, and the energy to mix, the energy gained by mixing, that gets combined into something called the heat of hydration. So that's separating the water molecules and then letting them interact with the solute. That's the enthalpy change that occurs when 1 mole of gaseous solute ions is dissolved in water. This is always largely negative. It's a big negative number. It's an exothermic process of taking solute ions and mixing them with water. Because what sort of interaction do the solute ions have with the water? What type of intermolecular force? It's the strongest one. Ion dipole. When you mix the solute ions with water, you're forming the ion dipole forces. So this is always going to be a big number, and it's going to be negative. Because mixing this is because it's got those strong ion dipole forces, it's going to generate a lot of energy. So the other component that we're missing there is the separating of the solute. Separating an ionic compound into its ions is the opposite of forming the ionic compound from its ions, and so the energy is the opposite in sign of the lattice energy. It's just the negative lattice energy. So the heat of solution then is equal to the heat of the solute, which is endothermic. Lattice energy is negative, but this is the opposite, so it becomes a positive. And this is what we call the heat of hydration, and this is going to be negative. So the heat of solution could be positive or negative. It just depends on the relative magnitudes of these two different components. Here we've got heat of hydration. Let's see, where am I? So if we're taking solid potassium fluoride and dissolving it in water, separating that solid into the individual ions is the lattice energy. So the lattice energy for Kf is minus 821 kilojoules. The energy required to take them apart is plus 821 kilojoules. And then the energy that is gained through hydration is minus 819 kilojoules per mole. And what we're left with here for the heat of solution is plus 2 kilojoules per mole. This is going to be an endothermic process. If the magnitude of the heat of the solute is less than that of the heat of hydration, the process is exothermic, the solution feels warm. If these magnitudes are reversed, then it's an endothermic process and the solution feels cool. So when you dissolve potassium fluoride in water and the heat of solution is plus 2 kilojoules per mole, is that solution going to be warm or cold? Is the heat going out of the solution or into the solution? Delta H is positive. So the energy is coming into it, right? So it's going to feel cold.